Assalamualaikum everyone. My name is Ghoos. I'm a student of Mechatronics Engineering from American University. My ID is 180869 and I'm currently in my fifth semester. This project is for the course Microcontrollers and Embedded Systems and covers maze solving robot named Zumo. So let's just open everything that we need. So we have our Proteus simulation here. We have the maze that we will be solving our Zumo with, and then we have the code. I have exported the code into a main.ini file so that it's easy to read and explain. So let's start our simulation first. So as you can see, this is our, a very basic and simple simulation. We have our Arduino Uno here, and we have our Zumo robot displayed over here, and we have an SD card that we will be storing our all the logs in. Then we have a serial monitor to print all the data into, so that we can see everything on in real time. So this is the code, but let's open it in um, Visual Studio so we can easily see and explain it. Right, so there we go. And the code. Right, so let me just zoom in a bit so it's easy to read. Yeah, that's a bit better. All right, so first of all, from line 1 to 7 we have all the header files that we will be using for our project. They're all we have sensors. There will be a header file explaining all the sensors that we have, and then we have a class for reflector sensor array that is connected under the Zumo, and then we have the motors, we have the buzzer, and we have a push button that will be used as a start or stop button for our robot. And then we have the SPI protocol because we are using an SD card, and then of course we have the SD card library itself. So this Zoom reflection sensor array, you can say kind of robot thing or maze solver car, whatever you want to call it, is actually based off another example by Pololu. And they can be you can visit their website at this link, and they have all the description available there. All right, so let's just get right into the code. So this is our sensor threshold. So the sensor threshold is actually, you can say, okay, so our sensor gives us a reading between 0 to 1000 depending on how close it is on our line. Actually, let me open the maze. So yeah, so this is the maze that is provided by our instructor. So yes, this is what we will be using for our project, and we'll be using as a maze for our Zumo robot. So of course the robot is, let's say that is standing here. So the threshold is actually the threshold we have seen here is actually, you can say, the value from the reflectance sensor that we will use as a reference to decide whether the sensor is detecting a light or not, because there can be a noise. Of course it's an optical sensor. It uses light to detect whether a line is underneath or not. So there can be interferences from all the environmental lines and everything like that. There can be reflections and all that kind of stuff. So we decide on an appropriate value of the that should be considered as the base level, that if the value of the sensor is higher than this threshold, then we can safely say that the sensor is currently above the line. So after that we have the a macro named above line. So it is a simple macro. I'm hopeful that you are familiar with what macros are. So it is basically taking you can say a parameter named sensor, and then it is returning a boolean statement. So it's a boolean statement, and it is returning a boolean statement, boolean, you can say variable, as 1 or 0 if the sensor value is higher than the threshold value. So we have the threshold value, which is 300. All right, and then we get the value from our sensor, which could be 500 or 350 or 250 or 700 or anything like that. And if that value is higher than the threshold value, then we can safely say that the sensor is above line. So whenever you call this, you can say macro, we give it a parameter of the sensor value, and then we can, be rest assured, we can find out if the robot is above the line or not. Okay, so after that we have the turn speed. So turn speed is how quickly the robot turns left or right, or turns around to go back on its path. So that's the speed. We can manage that speed, or we can change that speed here, but we're not going to change it. We're going to keep it 200. And then we have the normal speed of, you can say, navigation. That this is the speed the robo progresses with. I wouldn't want to mess with it either, because it can cause all kinds of weird problems and issues. And then we have a variable named line thickness. So this is a variable that will be, defining how thick the line is. So you can see here in this, so this, the thickness of this wall is like this one. So if we create a new line, or if we added this line, or if we want to create our own maze in Microsoft Paint, which we can do, I'm not going to do that today, but you can make your own maze in Microsoft Paint or any other painting software, and then you can import it here, and the Zumo will be able to, you can say, progress on it. So you have to define the width, how wide that line is here. And once that, after that we have z units conversion. So actually, z unit depends a lot on the voltage and the battery level and all that kind of stuff. So it's actually, when we set a speed, when we set, the speed of it, you can consider it as units can be considered as, you can say, a unit of distance covered by our Zumo robot, and that distance per second is the distance per second, and that depends on how many, how well the battery is charged, how strong the motors are, and things like that. So it can vary. It can vary depending on, you know it can vary depending on all those factors. But if we just deplete the battery half to its 50%, and then we measure it, then 1 inch is roughly equal to 17,142 z units. Okay, so after that we have another macro called overshoot. So overshoot is a pretty, you can say, a simple macro, of course. Okay, so you see, when the robot is traveling, let me open this diagram here. So let's say our robot is traveling here. Actually, you know what? Let me just draw it here for you. So let's say thickness. Let's turn it down a bit and change the color to red. So let's say we have the robot here. Okay, and it reaches this intersection, and it has like the sensors, a sensor area like this. Okay, you get the idea. So let's say, the sensor we have here. Okay, so the robot can, when it reaches an intersection, it detects a line there, and if we can't be sure whether it is actually a line, because a robot, it doesn't have eyes, it is not as smart as you and myself. It doesn't know better. All it knows is the values that it gets from its senses, and then it has to decide whether or not it's on the right path or not. So depending on that, we have to, you can say, um, implement some precautions and implement some extra steps to make sure that the values we are getting from our sensors are actually the values that we need. All right. So the sense, what the robot here, what the overshoot here does, the macro overshoot here does, is that it moves ahead from the line after it has detected something on the line. So it goes above, and let's say our you can say our robot, or you can say our sensors misbehaved, or we encountered an error, and the sensor has started malfunctioning. All right, so it starts giving false signals, and it starts telling a robot that, hey, there is a line ahead, while there is no line ahead. So what we can do is, we can wait a little. All right, so if the sensor has actually malfunctioned, then the robot will always be getting that there is a line ahead. All right, so in that case, if the robot, let's say the robot moves ahead, right? So the robot came over here, right, and then it moved, you can say the robot came up to this point, and it started detecting a line, and then it started malfunctioning. So as it gets off the line here, gets off the line, and the sensor is still malfunctioning, so the robot will still be getting the signal that there is a line ahead while there is no line underneath. So in such a scenario, we need to make sure that we don't make a wrong turn. Or if, let's say, the robot was here, a robot was at this position here, and the sensor started misbehaving, and the sensor started telling the robot that there is a line ahead, while we can see there is no line here, but the robot can't see, right? It doesn't know. All it knows is the sensor values and data it is getting. So it doesn't know that there's no line here, while the sensor is telling it that there's a line here. So what it can do is it can move ahead, so it can overshoot. Notice the word, it can overshoot from its position. And if the data, because common sense says that if there is a line ahead and we know its thickness, and then after a particular time, after you can say a split second or half a second, we should be off the line. The sensor should get off the line. They should be off. They should not be on the line still after a particular amount of time. But if the sensor still detects a line, then of course we can conclude that there is something wrong, because it shouldn't say a line. There's a line after a particular distance, right? So if there is still a line, then we can rest assured that it is false. So how the overshoot is calculated? Overshoot is actually, you can say, overshoot is actually used in the sense of microseconds. So we take the parameter of line thickness, and then we multiply. So we have the line thickness in centimeters or inches, right? You can see here, thickness of your line in inches. So it is in inches. So we multiply the line we have, the thickness we have, to inches with the unit conversion from inches to Z units, and we get the data for in Z units, and then we just divide it by speed to get the seconds that we will be needing for our, you can say, overshoot value. And then we have defined our button pin. So it is the pin here. You can see the pin for our Zumo robot, which is pin 4. And then we have defined our buzzer, and then we have defined our reflector sensor arrays, and then we have defined our motors, and then we have defined our push button on the button pin. Okay, so it is just a constructor with a parameter of integer that takes the pin number of the button and initializes it. So that's what we did here. And then we have some variables for our SD card. Actually, let me just check if the video is still recording. And oh yes, look here, we're recording. Okay, so we have the chip select variable here, and we have connected it to the pin number 10. We can see here the SD card is connected to the IO10. The chip select pin of the SD card is connected to the input GPIO pin 10. So that's what we have here. And after that, we have defined two files for our, you can say, logging. One is the my file. I named it my file. It is just a random test file. And then we have another file named log file, in which we'll be logging the movement of our robot. All right. So after that, we have a 100-character array named path. So the path is what we will be storing all the information that we have about it regarding turns. So let's open the maze here, and let me remove all this for you. Okay, so of course, so when the robot comes here, it reaches this point. It has two paths. It can either go this way or it can go this way, right? So if it turns left from here, the robot needs to remember that it turned left at this intersection, right? So that's what we store in this array. I'm sorry about that. So this array stores all the values, all the turns. They're usually just letters named L, R, S, and B. So L is for the left, R is for right, and S is for straight, and then B is for turning back. So that's what it stores here. And then we have another variable named path length, and as the name suggests, it stores the length of the path that we covered. So currently, there are no you can say no steps taken, and our path has 0 you can say turns in it. So the path length is 0, but we increment this value every single time we take a turn, so that we can count how many steps we have taken so far. So after that, we get into the setup. And then of course we begin the serial communication, because of course we need to print, we need to use the serial monitor here, so we print the values and all that. And after that we just print that we are initializing the Zumo mesh solver, and then we leave a line for statics and stuff. And after that we define an array of six, you can say six integers. It's an integer, so it isn't unsigned, because of course it cannot have sign. The sensor values don't have sign. They are either 0 or they are all up to 1, depending on the value. So it is it is 6 because we have 6 sensors on our Zumo. You can see here we have 4 in the middle, and then 1 on the right and 1 on the left. And then we have the account integer, you can say count variable, and it is simply to it is a random variable that we will be using in our, you can say, progression and loops to keep count of random you can say integers and variables and all that. So it's just a random variable. And then we have the last status. So last status is actually uh, a small variable that we will be using to store the information of a sensor's last status. So the status here is whether you can say a sensor is on the line or not. Right. So let's say our sensor has reached this point. All right. The robot is here, and we have all these sensors here. All right. So the robot is here. And let's say, okay, so let's choose this sensor here, this one, the leftmost one. So the status of this one is 0. So by 0 I mean it is not on the line. So when our sensor is above the line, we will say that its status is 1 or high, and when it is not above the line, we'll say that the status is 0. All right. So that the status of the sensor is 0, and when it gets over here, it moves ahead a little. All right, so let's say it moves up like this. It has moved here now, so the sensor will be detecting something, and as a result the status of it will change from 0 to 1. And but we're saving we have this variable to save its last status. So it will be used to compare whether sensor has moved from a line to no line, or from no line to on, or from to on to the line. So that's what we will be using this variable for. And then we have the turn direction, which is 1. So 1 is the clockwise direction, so we will be using this variable to declare whether the robot will be turning clockwise or counterclockwise on our, you can say, maze. So if the turn direction is 1, then it turns this way, and if the turn direction is -1, so -1, it turns counterclockwise like this. All right, so then we play the buzzer. Okay, it's a simple you can say a string of characters, and the buzzer understands it and plays different voltages, sends different voltages to the buzzer pin, which is actually 3. So you can see the buzzer pin is 3, so it sends different voltages with different you can say time differences to play the following tone, or you can say the music. And after that we initialize the sensor array, reflector sensors. And once we're done initializing our sensors, we set the motor speeds to 0, because we don't want our robot to be moving before its time. And then we just give a delay, small half a second delay to our robot. And after that we start so a 13 pin has the built-in LED, you can see here. So it is the pin number 13 LED. It is the built-in LED of the Arduino Uno. So we set it to high to indicate that we are in calibration mode now. Alright, so what the calibration does it's going to read all the sensors, and going to make sure that everything is working fine before the robot starts moving, before the Zumo starts moving. So, and then this line here, button dot wait for button. So all it's going to do is it's going to wait for the button to be pressed. So even once we have started the simulation, I'm not gonna start it now, but once we start the simulation, the robot isn't gonna do anything. It's just gonna stand still until or unless I press this button here. So that's what this line is doing. It's just gonna pause the robot at its current position and wait for the button to be pressed. And once we press that button, we're gonna move ahead, and then we print that we're gonna initialize SD card, and then we define the chip select pin as an output for of the pin. and then we go ahead and okay. So st begin is a small function, you can say. It's a very simple function that initializes all the pins. So we have the Misumossi and sequential clock pins there, and the master outs, slave in and master and slave out pins. So it it checks the connections, it checks for the wiring, and make sure that everything is working correctly, and everything is in order and all that. And once that's done, it returns either a true or a false, or you can say a high, low, or you can say a 1 or a 0. So if everything goes according to the plan and according to and everything's working perfectly fine, the SD begin returns a high, or you can say 1. So if it has succeeded in configuring the SD card properly, it sends a high, and as a result, this block will be executed, informing us that the SD card initialization has been completed. And if it doesn't send a high signal, in case something goes wrong, or if there's some wiring connection, or that's that got interrupted, or the pins are not configured properly, or anything like that, it sends a low, in which case we will be informed that the SD card initialization has failed. And once that's done, once we have begin our SD card, and once we have initialized all the features and all the functions of it, we can go ahead and open a file into the my file variable. Okay, so this is the name, it's just a random file that I've created, and we will be using it with the, you can say, permissions of writing. So you got to define whether you're opening the file with intention to write or read it. It depends, so that the code knows what to do, and the everything. So this is this simple function opens that current file into the variable. So now we can we can say manipulate this file using this variable here, and then we go ahead and see if the file is available. Okay, so if the file opened correctly and everything is working fine, and the file exists or not. Okay, so about existing. So if the file or file named random.txt already exists in our SD card, then it will be opened. And if it doesn't exist, or the robot, you can say the code, or you can say the Arduino cannot find it, the controller on the SD card cannot find that current file, the named file, then it will create that file. It will create a fresh copy of it. So either way, we are gonna have a random.txt file, whether it already exists or not. So once it has opened properly, we will have there will be a high, you can say, a high status here. So in which case this block of the code will be executed. And if there if there was some error opening the file, or if it doesn't exist, or if the you can say the controller cannot, for whatever reason, cannot produce that file on its own, then it's going to throw an error that the file initialization has failed. Otherwise, if the file does exist and it has opened correctly, we are informed that the file writing to file has initialized, and then we print it. So it is my file that println, so we're printing to the file that we have opened. We print that random text test. So it is just to make sure that the file opened. We can open and close files, and we have we can print to it, and then we are informed that the writing to file has been completed. Oh, and before we do that, we also close the file. All right, so the controller can only open one file at a time. So you cannot read more than one file at a time. So every time you open a file with st.open, all right, we have to close it as well. So every time we're done dealing with it, every time we're done writing to a file, we have to make sure that we close the file. Otherwise we can encounter all sorts of error where the microcontroller doesn't know what file to write to, or what's going to happen, and it can destroy our data or corrupt our files and logs and everything. So we need to make sure that we are opening and closing files properly. So after that, we open the file named Zumo path into our log file variable. So just like we opened the random text file, and similarly, if the file already exists, it will be opened, and if it doesn't exist, then it will be created and opened. And then we print into it that we print that the path is now starting. So this is where we'll be logging, and then we leave a small line here, and then we close our file. So that's it. And then we just print two empty lines on our serial monitor, because, well, aesthetics. All right, so this is, this for loop is where we will be. Okay, so sorry about that. So this one, so this is where, the whole calibration of our code will be taking place. Right. So let me explain. Let me start with explaining this. Actually, let me make sure the video is still recording. I'm actually a bit paranoid. All right. So it's still recording. Okay. Cool. All right. So the turn direction here. So you can see we said, okay, so we multiply the turn direction with -1, and then we override the turn direction itself. So if we have, turn direction is turn is already equal to 1, well, it is gonna turn into -1. And if it was -1, if it is already -1, then multiplying it with -1 will make it 1, right? I'm pretty sure that that should be pretty clear. Anyway, so that's what's happening. So if the turn direction is 1 by default, so it is not 1 now, because after executing this line of code, it's going to be counterclockwise. All right. So but if it is 1, then it's going to turn clockwise, and then if it isn't 1, then it's gonna turn counter. If it is -1, then it's gonna turn counterclockwise. All right. So as I explained here, if it is 1, it's gonna turn clockwise, and if it is -1, it's gonna turn counterclockwise. Or you can say it's gonna turn left when it's -1, and it's gonna turn right on the line when it's 1. All right. So we are simply multiplying the turn direction variable with the turn speeds. So we already know the turn speed to be 200. All right. So this simple function here sets the speed. So this you can say variable here, or this parameter here, is the speed of the left motor, and this parameter here is the speed of the right motor. Okay. So when we do this, the turn direction speed is, it's -1, right? We have established that it was 1 before. You can see here, let me just scroll up. So turn direction is 1, and multiplying it with -1 equals the result of -1, right? -1. So the speed of -1, so it's -200, and this one here will be positive 200, because -1 by -1 is a positive 1, and a positive 1 by 200 is still a 200. So that's how this is. And once we are done with this, all right, so what we do here is we are setting the turn speed of the left motor as negative. All right, so you can see here, let me draw it here. So let's say we have the Zumo here, right? I'm sorry for my drawing, I'm not the best artist. So the turn, you can see the speed of the so it's -1 and 200, so the speed of the motor is -200, so it's going to rotate backwards, right? So it's going to rotate backwards like this direction, and the speed of the right motor is going to be positive, so it's going to turn upwards, right? So it's going to turn upwards, and you can see, if you can just you can see that the robot is going to turn this way. And if you place it here, all right, so if you're placing it here, -1 is going to yield the result of this, like this. So as you can see, it's going to turn this way. Actually, it's getting a bit clunky. Let me remove all this. Yeah, just a second. So you get that right, hopefully. I'm pretty sure you get it. So that's how the robot turns clockwise or counterclockwise. And similarly, when this value will be a positive 1, when turn direction will be positive 1, then this one is gonna turn higher, and this right one is gonna turn low. So the robot is gonna move like this. And okay, so then we have a small while loop with a count variable. So currently the count is 0. You can see, I mean, where is it? Yeah, 0. So currently the count is 0, so obviously the while loop is gonna start. And then we calibrate our sensors, the sensor array. We're calibrating it. Just a second. All right. And then we have a function called read line sensors, right? So this line is actually just gonna read the values of the sensors, and it's gonna store those values in the array that we've created. So let's say we have a line on the the middle two ones in here. If we come over here, so we have a line on the sensor, this third sensor. Okay, so the numbering for this, you can say the array goes from 0 to 5. So this is sensor 0, this is 1, this is 2, this is 3, this is 4, and finally we have the fifth sensor here. Okay, so if we have a line under sensor 2 and sensor 3, so this is what our arrays is gonna look like. So after sending this, so this is the array we have, which is defined over here. So we have an array of 6 values, right? We have of 6 you can say entries. So after running this line of code, the we will have as sensors. Sensor will be like this. So we will have 0 0, and then we have 1 and 1 and 0 and 0. So this will be the state of our sensor array after running this line, in case the line is under, yeah, if and only if the line is under the sensor 2 and sensor 3. Alright, so this is that's what this line is doing. It's reading the values from the sensors and then storing them in the array we have declared. And after that, we have a small, you could say, I'm sorry, what? My bad. All right. Okay, so we have a small, you can say, conditional, and sure, you can see that if the time direction is less than 0, which in this particular case right now is true, because you can see that the sensor is the sensor we have here is the direction we have set here is currently -1, like for the first loop of our the for loop for the first time, and the first iteration, you can say the turn direction is -1, so obviously it's less than 0, and as a result this block will be executed and the rest of it will not, yeah, because that's how if and else work. So we get over here, and we have this macro called again finally. Actually, let me, I guess I'm, yeah, so we have this macro here. All right, so let me open. Okay, so what this is doing is above line, it is actually checking whether there is a line above the sensor 5 or not. So sensor 5 is this rightmost one. So you can see that the robot is when this you remember, right? When there is let me open the picture here. So when the robot is turning clockwise, there's gonna be a time. Oh, actually it's razor, my bad, so better. So there is gonna be a time when the robot turns like this, right? So the rightmost sensor is gonna be here, and then we have all the other sensors like this in line, right? So the rightmost sensor is gonna change its status, if you remember the status that we talked about just a while ago. So the rightmost sensor is gonna go from no line onto the line and then off the line, right, when it's turning counterclockwise. So the sensor is gonna go from status of 0 to the status of 1, and then again the status of 0, right? Yeah, I'm sure. So what it is doing, this is checking whether the sensor is above the line or not. So let's say, for the sake of our argument, let's say the robot is, on that, you can say, on the line. All right, the sensor has gotten onto the line. The robot has, rotated enough for the sensor to get on the line. Right. So and then we have this XOR operation, and with the last status. So the last status of this sensor was 0, right? The sensor was not on the line before. All right. So we have a 0. Okay. So this statement, this whole statement, it's an XOR statement. So what that means is that we're gonna get a high. So it's a kind of a boolean. So we're gonna get a high when these two values are different, and we're gonna get a low when these values are not different. All right. And let's say the line last status was 0, the robot was not on the line, and then this one here is returns a 1 because the sensor is now on the line. So we have different values here. We have a 1 here and we have a 0 here, so we have different values. So this statement is going to return a 1, which will be added to the count. All right, so let's imagine, for the sake of the argument, we say that this returns another 0, or this returns a 1 again. Once it's been on a line, it returns a 1 again, and the last status of it was 1 because it has added 1 to it already. All right, so this time there's no change. This is 1, this is 1, and this is 1, or this is 0 and this is 0. This situation is the same, so nothing is gonna be added to the count, right? So we can say that here the count will be increased every time the the sensor goes from no line to the line, or from the line to no line. And it is, said pretty simply here. If the most right sensor changes from over white space to over line, or over line to over white space, we add 1 to the count. All right. And yes, of course, that makes sense, right? And then we just update the last status with, you can say, the current status of the line, because in the next iteration the current status will be the last status and the future status will be the current status. You get how it is. So that's what we're gonna do. And if we see here, the sensor, the status is gonna change twice, right? So it was 0 here, it was, you can say, 0 here, and when it got on the line it was 1. All right, and then since it gets off the line, it's going to be 0 again. So it changes from 1 to 0, 0 to 1, and then it changes from 1 to 0. All right, so we have 2 changes, so the count is going to increase twice. All right, so what we're checking here, so we set the counter to count is less than 2, so we are checking until the sensor has crossed a line. All right, and once it does, the while loop is gonna break, and we're gonna get out the while loop, and then the counter is gonna be set to 0, and the last status is gonna be set to 0, and then we go up here back to the loop, to the start of the for loop, and this time the direction is gonna flip, because it was turning clockwise. All right, so it's gonna change its direction as a result. And so once we have reached this position, the sensors have the rightmost sensor has crossed the line, the direction flips, and as a result the robot starts turning this way. So you will see that when we start our this robot, you can say, flickers right and left, or clockwise and anti-clockwise on its main position a few times, like 3 to 4 times, and then it starts moving. So this is what it's doing. It's calibrating the sensors, it reads the values, all right, and then this loop just runs until the rightmost sensor is off the value. You can say the rightmost sensor is off the line, and then it flips direction, and it does the whole thing 4 times. So the loop runs from 0, then 1, then 2, then 3. So that's 4 times. So the loop runs 4 times, and it calibrates the sensors properly to the line, and that's what it's going to do. And then we call it to turn to left. All right. So what left arrow does? Okay, let me show you. So when we are finally done, like when we're done, calibration is done. Yeah, because we have run it 4 times. So if we run, let me show you. So when the calibration is done, the robot is gonna be in this position like this. All right. So this is gonna be the final position of the robot. And of course we need it to turn left, right? We needed to get it back on the line. So we make it turn left. If we had if we change the time, we can, let's say, if I write 5 here or 3 here, then I'm gonna have to make it turn right, because then after the calibration the final position will be here. So if I make it 3 or something, then the final position is going to be here, and then it's going to need to turn to its right to get back on the line. All right. Okay, so with that out of the way, actually, you know what? Let me explain how the turn function works here. Where is the turn function? Here it is. So here's the turn function that you just saw. So it gets a character, you can say, parameter. So the parameter can be either L or R, left, right, straight, or back. Okay, so of course we can define some of our variables that we will be needing, and then we define the count variable, we define our last status variable, and then we define our sensors that we will be using to store the values. All right. And since they're local variable, since the sensor is a local integer, we need to define it every single time. Unfortunate, I know, but we can't find a better way to do it. So I'll explain why the case L and B are the same in a minute. So it is pretty simple here. You see, you turn the motors. If you need to turn right, you move the left motors backward and right motors forward. And as I explained, like here, left motors backwards and the right motors forward, and it's gonna give it a left turn. So that's what it's doing. It's just in turning it left, and we have this again, the same while loop again, and it turns the left motor. Okay, so this is the same loop, but it's got a different sensor here. Okay, so we have a sensor. We read the values from the sensors. Of course, we need to read those values in order to evaluate them, and then we check if the status of this. So it's sensor one, so which is this one. All right, this is the sensor that we're checking this time. So we're checking if this particular sensor changes its status. So I hope I don't have to explain this whole thing again, because we just explained. So the counter will be increased if the status of this particular sensor, this sensor one, it changes from 0 to 1. Okay, so that's what's gonna change. And if that happens, if the sensor, if this particular sensor moves from the line, it's like it moves from, you can say, so it was here, right? This left sensor was here. Let's say this is the leftmost sensor, this is the second sensor, then this is the third one, this is 4, this is 5, and this is finally the sixth sensor. So it needs to change its status enough, right? So we have 5 lines here, we have 6 sensors here, right? So for the we can see that for the sensor to make sense, the line needs to be under these two particular lines, so the middle two ones, right? So just a second. So the line needs to be under these middle two sensors, and that's only gonna happen once this this second one, the sensor, has crossed the line. So if it crosses the line, then we can be sure that the middle two sensors are gonna be, the two sensors in the center are gonna be above the line, right? So that's what it's doing. It's checking if the second sensor from the left has crossed the line, and once that's done, it breaks. All right, sure, and it breaks. We've turned left or right. We've turned left or right, and yes, the function is called off, and we have turned left already. And after that, if we have to turn right, right, if we have to turn right, then of course we turn the left speed down. So we make this one here. So this time left motor is gonna be high and this is gonna be low, and as a result we're gonna turn this way, and that is gonna be right. So this time we're gonna turn right with this code, with this by setting the speeds to this one. And once that's done, we're turning right now, and similarly we're gonna read the sensors, right? We're gonna read the sensors, and then we're gonna check the fourth one, the fourth sensor 4, which is this one. So since we're turning right, we need to make sure that this sensor crosses the line, and once this sensor crosses the line, we will be sure that the line is at these, the two center pieces, the two central sensors. So that's what we will be looking forward to. Once that's done, we break the case and we're out. And if it has to go straight, well, of course it's going straight already, right? So the robot is moving straight ahead. So that's because the robot is here and it's gonna be moving forward. Both mode is moving forward, so it's gonna move forward anyway. So if you have to move straight, then just don't do anything, okay? Just let the poor thing do its thing. All right. So oh yes, so let's get to the back one. So why the back has the same logic as left? That's pretty intuitive and simple. Let's say the robot has reached here. All right, let's say the robot is here. So now it cannot detect any lines, right? It can't see any line here. So what we're gonna do is we're gonna turn this left motor down, and this is gonna turn up, and this is gonna turn like this. All right, and when it is about to reach this left sensor, this one is gonna click here first. All right, so if this sensor, if this sensor is going like this, and then it crosses this line, left sensor crosses this line, we can be rest assured that these two sensors are now above the middle line here, right? So we kind of have turned left, right? We turned left, but we turned back, like we turned left until we were back on the track. Oh, that rhymed, nice. So that's what's happening here. All right, so that's why we have the same, you can say, logical code for both left and the back case. All right, so that's how we our robot turns. And well, let's get back to our setup. That's where we were, right? Yes, we would turn. Okay, so as soon as you've turned the left, from a logic, from a setup function, we set the speed to 0. All right, we make the speeds 0, and we play a small buzzer sound indicating that we are done calibrating. So it was just calibration until this part. All right, the whole setup happened at this part, and then we set the pin to low. All right, so once the calibration is done, once the robot is out of calibration, we can turn the functionality off. I'm sorry, I'm yawning. Okay, so after that we have the function called solve maze. Okay, so this is the function that's gonna solve every segment of the maze until we get to the finish line. So let's get to it. That's very intuitive and simple, you can see. So the very first thing, okay, so you can see in this function we have a while loop. All right, while one, and it is only gonna break with a break statement, which we can find here. Right, so intuitively, if this block ever gets called, we're gonna get out of the while loop, and it is only gonna get called when this maze has been solved, and I'll show you how. Okay, so the very first function is follow segment, so I guess let's move to follow segment. So where is it? There it is, little one. So the follow segment, so we have the integer position integer, and then we have a variable for our sensor values, of course, and then we have an offset from the center. All right, and then we have an integer claiming the power difference. So the power difference will be the difference between the power of our two motors. All right, so firstly we do what we do is we make a we read the values from the sensors. Okay, so this line actually reflectance sensors from dot read line is equal sensors actually does two things. So one thing is the one we explained here, and I don't know where it was, I don't remember anymore, but you get it right. The one thing it does is it reads values from the sensors, and it stores them onto the SD, it stores them on in the particular array that the sensors were written for, right? Actually, let me check if the video is still recording. It is recording, nice. Okay, so that's what it's gonna do, but it also returns a number. All right, so it returns a number from between 0 to 6,000. All right, so let me show you here. Yes, here. So let's get to the QTR senses. And not header file, we need to get to its actual code. So we have a function here called readLine. Let me move down. Here it is. So a very simple function here named readLine. So what this function does is it, of course, writes the values and it returns the last value and whatever. So it returns the last value. So that's the value it will be returning. But it also, you can say modifies the array we have set. You can say written. The array we have, what is it called? We have passed on to the function. Yes, the array we have passed on to the function. That's what it's gonna do. Okay, so the very first thing it does is it gets the average of all the sensors, and then it divides by the values of them. So let's say that okay, actually let me just open a blank. What do you want me to open? I can open Microsoft Paint. Oh, look at that, we're on Paint. Okay, so let's say that we have this normal function with multiplied by the sensor of the value 1. So let's say we have values, we have sensors 0. Okay, so 0 means 1, 0 means no line, and then we have line here, and then we have a line here, a line on these two sensors, and then the rest are zeros. All right, so the function here you can see here in this code is we multiply the first 0 with the first value, 1000 with the second value, and then 2000 with the third value. All right, and so on and so on. All right. So let's say that we have this one, right? So this is gonna be 1000 plus, so this is gonna be a 2000, right? And then we have we divided by all the values we have under here. So we add all these values, which turn to be, well, 1 and 1 are 2. So we divide it by 2, which gives us a value of 1500. All right. So what this means is, okay, so we got a value, we have got return the value, this function here. So this is the last value string. This is whole, this is the one, like the sensor has loops and all that, but finally it comes down to this last value that it's all right. So it gets an average and then it divides it by the sum. Okay, so that's what it's doing. And once we have that value, okay, so let me write it here. So we have 0, which is nothing. If it is 1000, then we can rest assured that the sensor, the line is under the leftmost or sensor 0. And if it is you can say 1500 as we got, then it is the line is between those two sensors, with the leftmost one and the middle one. And if we have a value on you can say 2000, then it is on the sensor 2, and if it's 2500, then it is between the two sensors, and so on and so on, right? So in the middle, like when we have in the middle, so it will be between the sensors 2 and 3, right? So you can say in this diagram or in this Proteus simulation here. So here if we have the so this will be if we have a line here, both here, so this is gonna be what, 1000, 2000, and this is gonna be 3000, right? So 3000 plus 2000 divided by, well, 2, because these two sensors have a high value. So 5000 divided by 2 is 2500. So whenever the line is in the middle, like whenever the line is on the center, we're gonna have a value of 2500 here, right? I hope that makes sense. So we get the value here. We get the we get whatever position value we get from the formula that we just discussed, and then we calculate the offset. And how we do that is we convert this value into position integer. So this may not be an integer, okay? So it may turn into a float or something. So we convert it into an integer, and since it was an unsigned, it can be positive and negative. So we need to make sure that it is turns out to be something. As a result, we subtract 2500 from it. So let's say you can say if it is exactly on the line, if the robot is exactly moving straight on the line, then the position value will be 0. Oh, sorry, the offset will be 0, because position will be 2500 just as well, right? So 2500 minus 2500 will return to 0, so the offset will be 0, which will mean that we are currently on the center. But if it is negative, then we can say that we are on the left, and if it is positive, then we can say we are on the right of the center of the line. And then we calculate the power difference that we will be changing for our motors. So the power difference is m1 minus m2, which is motor left minus motor 2, motor right. So we find that out by dividing the offset by 3. So that gives a proper estimate of the values that we will be sending to our robot. Okay, so now we need to find the actual power difference that we can set on our motors, because we can't set the motors to a negative. Let's say you can come here, you see this here. So let's say the offset position is 2000, right? So 2000 minus 2500 will give us a minus 500, and minus 500 divided by 3 will give us a negative number, right? We'll get, so power difference will be negative. And well, we cannot set the cannot set our robot to a negative motor speed, because then they will start heading backwards, and as a result they're gonna turn off, or they're gonna rotate. We don't want that. We want them to slow down. Okay, we don't want them to turn backwards. Okay, so we cannot give them a negative value. So what we do here is we check whether the power difference is greater than the speed. So let's say the speed is, if we have the speed of 200, so let's say the power difference is let's say 500 or something. All right, So if it is like let's say power difference is 300, so it is greater than 200, right? So we're gonna set the power difference to speed. So we just set it to 500, 2500, right? Okay, so 200, you can say if speed is 200, so we just set it to speed. But if the speed is, let's say the speed is the the negative turns out to be minus 200 or something, so it is minus 200 and it is less than you can say the speed. So we just set the power difference to the speed, because we're not gonna exceed our final speed here. We cannot exceed it. We're gonna stay under our speed limit. So if it exceeds the speed, we're gonna set it to speed. That's it. And now if the power difference is less than zero, if the power difference is, let's say, minus 200 or something, which means that the left motor needs to fasten up, and the left one speed needs to slow down, so that our robot can then get back onto the line. All right, so we add the final speed to this one, and we add the speed to the left motor, and we increase its speed so that it can get back on the line. And if the power difference is positive, which means that we need to turn the other way around, and as a result we will subtract the power difference from the speed of the right motor, so that we can get back on track. Like that, that's what it's doing. And then we have two conditions here. And let's say, all right, so we have the sensor here. All right, so we check whether okay, so above line checks whether there's a line above sensor 1, right? And putting an exclamation mark or not negative operand to it, we can declare, we can make its negative, we can make it's not operation. So if what this says, if this if there is no line above sensor 0, and no line above sensor 1, and no line above sensor 2, and so on until the last sensor. So if there is no line under above any sensor, so we can rest assured that the segment has finished. So in here, let's say the robot is here again, right? So let's say the robot has reached here, so there is no line under any sensor. So we can rest assured that the segment has ended. So this is the follow segment function, right? It is following a segment. So if you come here, so these are the segments. So this is one segment, all right, this is another segment, and this is the third another segment. So these are all different segments of our path, similarly like this one. And then we have this segment here. So these are all different segments of the part, and all this function intends to do is keep the robot following this particular segment. And as soon as the segment ends, we have to make a decision whether to turn right or go straight or something like that, right? So if we have a condition that if there is no line under any sensor, then we can we are sure that the you can say the robot has ran off the line, so the segment has ended, right? So we end it, we break the function, we return the function, and when you write a return function, the operator can say the function is terminated wherever it is, regardless of what was happening. It just terminated. So there is no line under it, the follow segment, you can say the function is terminated, or else there is line under a sensor left, or you can say this is the sensor right. So if there is a line under sensor right, or if there is a line under sensor left, all right. So if there is a line under here, so let's say the robot is here. Okay, let me erase all this segment thingies. All right, so let's say the robot reaches this intersection here. All right, so there is gonna be a line under the left segment, right? So if there is a line under the left segment, or if under the right sensor, this sensor is gonna terminate as well, because it will have found an intersection. So that's why it's stopping. Actually, let me check the recording again. It was recording, okay. So yeah, the segment will have ended and the robot will stop. Okay, so let's get back to the solve maze function. So you see, we follow a segment until we meet an intersection or a dead end, and then we have three more variables for finding left or finding right. All right. We turn they are 0 by default, because we conclude that there is no line under any sensor, but we read the sensor values and we change them accordingly. So let's say we have okay, we of course we define an array of 6 values for storing the sensor data, and then we read values. I've already explained this function. So we read values from our sensors and store them in this array, and then we check if we have a line, if the sensor left, so 0 is leftmost sensor. If the leftmost sensor is above the line, we set it to 1. right? And if the right sensor is above line, we set found right to 1, right? Okay, sure. I mean, that's hopefully pretty simple. All right, so once that's done, now we are okay. So we set the motor speed to motor speed. The robot keeps going forward. We haven't changed the speed. We haven't made any turn yet because we don't want to. We want to check if it's an error with the calculation, or if it's an actual, you can say an actual thing, an actual line. So we give it a delay of overshoot. So we're dividing, we overshoot. We already explained that. What was that? A macro. So we already explained this macro. So we divide. We wait for half of the overshoot. We don't read completely. Okay, we have wait for half of the overshoot time, and then we read the values again of our sensors, right? And then we check which of those sensors is above line, and if any of them is, we change the appropriate variable from found left or found right if any of those variables are above the line, sensors are above the line. And then we have here dived a little further. We will dive a little further again. All right, and after that we will just check for a straight exit, because we need to check if we have actually hit a line, right? So we read the values again, and then we take the values. Finally we take the values of the sensors. All right, so this is like the final value that we will be using. So we change them accordingly. If we found the left turn, then we make it right, make the left one higher. If we found the right one, make the right one higher. All right, so then finally we have this if segment here. So what we're doing is, let's say we have a sensor on, okay, so these are sensors. This is sensor 1, 2, 3, 4. So if any 4 of these sensors is above the line, we can say that we have found a straight one, right? We have found a straight path. We have a path ahead. If only the left one, or if only the right one found the line, then we would think that the sensor is going to have to turn left. All right. So if any of these 4 sensors finds a value, then we can say that we have a line ahead. But if all of the sensors, sensor 1, sensor 2, 3, and 4, all 4 of them find out that there is a line in front of them at the same time, then we have had a jackpot, because this is the only place that is wide enough to cover all 4 sensors, because this line cannot cover all 4 sensors. It will always be either 2 of them. So 2 are here, the 4th one is here. So it can only cover 2 sensors at a time at maximum, right? So if all 4 sensors are covered, which can only happen here, when we are at the end. So if only this if this happens, then we can rest assured that we have hit the jackpot, and we have reached this you can say our finish line. Then we set the motor speed to 0 and we brake. And if you remember, I told you that the only way to break this while loop is to actually call break operator. So if we have hit the jackpot, we can just stop, and this maze will be solved. And if that's not the case, if this loop is not run, and if we are not on our you can say the black spot, then we choose the direction, right? We have to select the direction we're going to choose. So we have this function called select turn, and we pass all our variables, found, left, right, and straight one. We pass all these for 3 you can say values to our select turn number, and then we change. Okay, so we select. Okay, let me get to it. Let me get to the select turn function here. So this is we pass out the left 3 parameters: found left, found straight, found right. And of course they're like boolean kind. Of course they're either going to be 0 or a 1. So if found left, which means that found left is high. So if found left, then we print to the serial that we're gonna go left, and then we open the Zumo path file. We print to the file that we are gonna turn left. We close that file. We print to the serial monitor that we have written to the file, and then we leave a blank line for statics. And if the file could not be opened, then we print an error that it was not locked to the line. and then we return the character L. So yeah, this will be returned to the function value. So the stack turn will return L if we found the left path, and if we didn't find the left path, and else if it's gonna run if the first one didn't. If we found straight, we're gonna print straight. We're gonna open the file. We're gonna print to that file. We're gonna inform that the file has been written or not written, and then we're gonna return S, right? And otherwise, if we found right, we're gonna print to the remember that we found right. We're gonna open the file. We're gonna print to the file, and we're gonna return the right character. And if none of them happens, if none of those three were right, it's because let me open this picture. So if a sensor, if a robot is here, of course it's gonna have to turn left, so it's gonna turn L. Here it's gonna turn L again, but here when it turns here, no left, right, or straight is found, right? So it's gonna have to turn back, right? So it's gonna need to turn back because we have hit a dead end. So that's why when it's back, when it is when it is none of the three, when it is neither left nor right nor straight, then we must turn back, right? So the last one is like else. Now we turn back, we return, go to we return, open the file, we write to it, and then we return the B character, right? Okay, so let's get back to where were we? We're on the solve mails, right? Yes. So we turn, and then we select the direction which one we have to turn. We save that in the dir character and the variable, and then we pass that to the turn function. And of course we remember the turn function, right? We just explained that here, how we turn depending on the character that's passed to the turn. And then we have so the path length is currently 0 because we haven't made any moves yet. So it is 0, and then we save that character into the path, into the placeholder here, into the position on the array, and then we increment the path at 1 plus 1. All right, and then we simplify the path, and see, is it still recording? Yes, it's recording. So we simplify the path, and then the maze keeps running until unless this block is called. So this whole thing keeps running again and again. We check the sensors, we check file left and right, we overshoot a little, we check for the values again, we select which turn we have to make, we change that turn, right? Then we save the value of the turn in our path, and then we increment the length of our path, and then we simplify the path again, and it keeps going and going and going until or unless we hit the final spot, until we have finally solved it. So we have the function of simplifying path here. So where's the simplifying path? Here's the function. So it's a pretty basic simple function here. Let me explain. So what this simplify path does is it solves the last three values for a simpler one, for a simpler path. All right. So if the path is length is less than 3, or if the path, the second path is back, right? So let's say the path length is, let's say 5. All right, so 5 minus 2 is 4 minus 2 is going to be 2. So if that was a back turn, then we're just going to return, because we can't simplify that one. So either if the path is less than 3, or if the path has B on its second to last turn, then we're just gonna return, we're gonna stop the function, we're not gonna simplify. But if the length is greater than 3 and the second last one is not B, okay, so second to last turn was not a B, then we're gonna have to we will just make it we will proceed with our function. So we have an integer here called total angle, so that's the total angle we'll be using, and then we have defined this integer I. All right, so this will be used for our for loop. All right, so we are solving 3 variables, right? We're solving the 3 ones. All right, so we are solving the 3 from the back. So we have a switch case, which okay, so path length is, let's say 5, so 5 minus 1 will be 4. So we check whether the fourth one is a right, you can say a right turn, a left turn, or a back turn. So if it is straight, we're not going to do anything about the straight angle. But if it's left, right, or back, then we are going to add the following angles. All right. So let me open this picture. Okay, let's check this turn. Let's actually let's see a lot of them. So let's say we are here, robot is here at this position, all right, and we hit an intersection, right? So we have on our path we're gonna have a right trajectory, right? So this is the x-axis, so this is gonna be an angle of 90 degrees, right? So if it was a 9, so if it is an r, we add 90, to the angle. And if it was a left one, which is gonna be, let me show you, oh sorry, it was a left one, my bad. So it was a left one, so we add 270 to it. I can, oh sorry, let me show you here. So it's a left one, right? It's a left turn here, so we add 240 to it, 270 to it. And if we have, let's say, you can say, what was it, if we make another turn, let's say, where's the picture here? Yes, so let's say we've reached here now. Okay, we have reached here, so we are here. Okay, so if we're gonna turn here, so this is gonna be an 180 degrees turn, right? So all these angles are gonna add up, and what we're gonna end up with is, if let's say we have, you can say, an angle of 90 degrees. Let me show you here. Let me simplify it for you a bit. So let's say this is an angle of 90 degrees, right? And here we have a picture, and this is another angle of 90 degrees on our path. Like we're going here, and then we have another angle of 90 degrees, and then we turn left from here, from here, because by default it turns to the left, so it turns here downwards. So this is an angle of another 90 degrees, right? And when we can get to this end point, we're gonna turn around, so that's gonna be a complete 360. Okay, and then we're gonna take another turn here like this. We're gonna have to turn again, so that's gonna be another 360. And then we come here, and then we turn left from here, right? We turn back, so this is gonna be another 90. And then we are here, and then we turn here this way, so this is gonna be another 90. And then we turn from here to here, and which is gonna be another 90, right? So let's add all these up. We have 1 2 3 4 5 6 90s and 2, so 2 360s, 2 360s, and we have 6 90s. All right, so the total angle gets to be, let me actually just calculate it real quick. So we have 360 by 2 plus 90 by 6. All right, and actually, let me mind it. So that's a total angle of 1260 degrees. That this is the total angle of this whole segment here. This whole segment has an angle of 1260 for our all turns. So if we divide that by 360, so it is, it turns out, we get a remainder of 180, right? So if we modulate it with modulus, if we take a modulus of it with 360, modulus 360, we end up with 180, right? So this whole, you can say, this whole segment of all these weird turns and all that, all those funky movements and all that. Let me remove all this just a second. I don't know if I'm going to remove it. Let me see. Can I include this here? Yes, just remove everything. So right, so the total angle here, from all these turns turns out to be 180, right? So what that means is, if we came here, and if we just took a turn of 180 here, 180 degrees here, it would be the same as moving all the, taking all these turns. So a 180 would be, a total of 180 will be like this, right? So if we just went straight from here, it will be the same as moving all those points here and there, because the end point is still the same. We went to the left, and then we took another left, and took another left, and we turned back, and then we turned back again, and then we took another left, and we took a right, and then we took another left, and then we took another right, and then we came here. So if we just went the same way, we would end up with the same result. right? So this is, we are simplifying the path here. We are adding all these angles, and we're taking the modulus of it with 360 to determine what should be the final, you can say, the angle at our intersection. And yeah, so then we pass on that into we replace the, we can say, the array with the path. We rename the path and all that, replace it. We, if the angle is 0, we set it with straight, and 80 when it is, is 0. So, and if it's 90, we replace it with R, and if it's 180, we replace it with B, and if it's 270, replace it with L. And at the end of this whole, fiasco, at the end of this whole, you could say, functions and all this, we have finally, gotten two less, you can say, paths in our, you can say, mm, we have gotten two less steps on our path. The path is now two less steps shorter. Okay, so that's how we simplify the path. And once we're done simplifying, let me get back to the loop thingy. So solve maze. So we have simplified, right? I guess. Oh yeah. So we're done here. So we go to let's get back to the loop here. So we have solved the maze, right? We have gotten to the end of it. We have simplified the path as well. So obviously we have reached the point. So we play this buzzer, all right? We play it. We play a sound, and then we print that we have solved the maze. And once we solve the maze, we open the log file, all right? We open the file in the Zumo path, and we, for our aesthetics, we leave a couple of lines blank. We write that we have solved the maze, and then we leave a few more couple lines blank, and then we close that file. And then we print to the serial, informing ourselves that the file has been written. And if we cannot write the file, we just log it as, not logged to SD card. And once we're done logging, we finally get into the another while loop, and this loop is gonna run forever until we reset the Arduino. If we reset the until we reset the Zumo. So this is gonna wait for the button, and the maze has been solved, the path has been simplified. Now all that's left is to move the Zumo back to its starting position, and get it back to the finish line. So we wait for the finish line to proceed, and once we've done that, we call the function of go to finish line, which is gonna let me go to it. And here we have defined the sensors. We have another I variable. So if path is B, we just turn B. That is not rocket science or anything. So then we have a for loop, and we don't have to define I, because we have already defined as I is equal less than 0. So we just leave it blank, and then I is less than path of length, of course, with whatever length we have, which finally turns out to be, it can be 10, it can be 50 or anything. I don't know the exact, I can't tell you the exact number right now, because it's arbitrary. So with the condition increasing, so we follow the segment. We have explained that, right? And we follow that segment. We set the motor speed to whatever speed we have, and then we overshoot a bit. And after overshooting a little, I mean, once we have hit we hit an intersection, or we hit a dead end, the follow segment function breaks, it stops. So we still have that, we still have the speed, and we overshoot a little. And after overshooting, we take the turn that our robot has at that particular position. All right. And once we have taken that turn, once we have followed all that, we just follow the segment to the final position. We keep following the final segment, even when we're done with the path. So the final, once we're done with the path, let me show the picture here. So once we're done with the path, once we reach this position, the path is gonna be all done. All right. So we just follow the segment until we have reached the end of the maze. So as soon as we get to these sensors values, this you can say final point, we're gonna read the sensors, and then we're just gonna set the motors to 0, and then we return the function, and the go to finish line function has been finished. It has finally reached its position. And once that's done, we display that we have reached the finish line. And once we've reached the finish line, we play the buzzer again, informing ourselves that the maze has been solved. And then this loop just keeps going. You can just pick up the Zumo and place it back on the position, and then bam, solve it all over again. And it will solve it as many times as you run it. Let me see if the recording still. Okay, it's recording. Okay, So I guess it's now time to get to the coding. Let me move it. And oh no, we're not gonna save it. My bad. So we're gonna erase all, and we're gonna close it. And you lost changes. Yes, we're gonna save without changing. So see, now our change is done to it. So let's actually, yes, let me close this too. Don't save it. So we need to create a file for our SD card. All right. So you know the file that we will be storing. Let me show you how to do that. So we have this software called WinImage that we can use to create blank images. So blank an image is actually, you know, just you can say an archive to store files. And so we create a new file and we set the custom image format. And well, we don't have to change anything here at all. Right, you just click OK and it has created a blank image, and then you save it. And I'm gonna save it to desktop and Zumo, and I'm gonna name it, you know, we change the file extension to 0. Let's name it SDA. I'm gonna name it SDA. Okay, it has been saved and you can just close it now. All right, and if you open Zoom, you can see the file has been created here. Okay, cool. So we're gonna go into Zumo. We're gonna select our SD card. We're gonna go into properties. So we're gonna click here, and we're gonna go to desktop and into Zumo. And we're gonna, okay, so you can't see that file here, you know, regardless of what, you can't see that file. So what you're gonna do is you're gonna type an asterisk here, and that's gonna bring up all the files. Then you're gonna select the sda.ima file, that is, you know, our virtual, you can say, card. Then we click OK, and then come here and you select the maze that we're gonna run. So this is the maze that provided by our instructor. So we open this one and we click OK, and let's, you know, make sure everything is done fine. And then you just well, let's start the simulation here now. Just give it a second. I'm sorry. Oh yes, so it has this weird problem where it gives us an error of including server, but if you just, you know, build it again, so we have to build it twice for whatever reason. So now it's compiled successfully without any errors. I don't know why that happens. Just, you know, some stupid limitations of some stupid software. That's a good software though. Okay, so we start it now, and you can see it has you know, initialized. Let me make this window a little larger. I hope, you know, it doesn't matter. So let's start it. You can see initializing SD card has initialized. It has written to the file and completed, and now it is logging and writing to the file. Turns left and then left again, then it goes straight and it turns left again. So just, you know, let it go. Let's let it solve the maze now. And you can see, you know, we have solved the maze, right? So we can just grab the Zumo and place it at the start line, and we press the button again, and this time it's just gonna, you know, it has already solved the maze, right? So it's gonna go to the path that is just, you know, the right one. And you can see it has reached the finish line. It didn't have to go all the way to this section or this section because it knows that's not, you know, the final position. All right, so that was the simulation, and I will have to actually close it to show you the results. So we're gonna go here into the Zumo folder and we're gonna open this file. Okay, and you see now we have this both Zumo path and random created here, so we can just click them and we can paste them here. All right, and you can see it's just a random test. That's what we wrote in this file. Not bad. And then we have the Zumo file here. So it was the start of the path, and then it has all the whole, you can say, the log here. It's printing all its movements and steps, and then once the maze was solved, it printed that the maze was solved, and this is the file we get. So I guess that will be all for today. Thank you for coming to my presentation, and yes, see you around. Khudafez.